So, students, in this video, we will be talking about photoelectric effect, and this effect is basically the further confirmation of particle nature of light. So, how do we define this photoelectric effect? Basically, it's a phenomenon of ejection of electrons. If we have a photosensitive metal, and uh, if we apply, say, ultraviolet rays on this photosensitive metal, the electrons are ejected. So this phenomenon of ejection of electrons from the metal surface, when the light of some suitable frequency or wavelength falls on it, we call this thing as photoelectric effect. So the point is that if I have to generalize this thing, that what I'm talking about is that when we have ultraviolet light incident on some negatively charged uh, some plate, some photosensitive plate, say zinc plate is photosensitive, and if we allow the ultraviolet rays to fall on this negatively charged plate, what we observe is that there is the loss of charge, and this loss of charge is due to the ejection of electrons. So if we have this as a zinc plate, the light falls on it of some suitable frequency, the electrons come out of it, so there is some loss of charge. So this kind of effect we call as photoelectric effect. And all substances, I mean metals as well as non-metals, give out slow moving electrons when they are illuminated with the light of suitable wavelength. So you can see here I have sketched out an experimental setup for the photoelectric effect. And to move on with our introduction to this effect is that the electrons that we have that are emitted from this metal surface, these electrons are called as photoelectrons, and the value of charge and mass, the ratio between the charge and mass of these electrons is same as that of electrons that are produced by other methods, by other techniques. And if we talk about alkali metals, this alkali metals like sodium, potassium, sodium is there, potassium is there, cesium is there. They are sensitive even to the rays from the visible part of the spectrum, right? And whereas talking about zinc, cadmium, etc., they are sensitive to ultraviolet light alone, right? So light of shorter wavelength has more energy and is thus more effective in producing the photoelectrons. The effect is this effect is also observed in non-metals. So that's what I said in the beginning. This effect is also observed in non-metals, but as they are highly electronegative, waves of short wavelength are required for photoelectric effect to be observed in liquids and even in gases. In gases, the phenomenon results in the process of ionization. So this is the experimental setup. We have an evacuated tube. We have a photosensitive plate. This is interchangeable high tension battery where we can change the polarity. And here we have the collector of the electrons that are emitted. We have some light falling on this photosensitive metal, and we can measure the voltage and we can measure the current. Now, to discuss the very first important parameter of this experiment is that when we have this light of suitable frequency, when it falls on this on this plate, uh, which is named as C in our case. What we see is that there is ejection of electrons, and these electrons are attracted by the positively charged plate, and then we have a measurable photoelectric current that can be measured using this emitter. Now, the very first important thing we would like to discuss that we observe from this experiment is the effect of intensity, effect of intensity of light, or I should say radiations, light radiations. Okay, so what we choose in this case is UV light, okay, ultraviolet light of some fixed frequency, and this light is allowed to fall on this plate, and the collector that we have here, this collector plate is kept at some positive potential with respect to the high tension battery here, right? And with respect to A, so the value of this potential is adjusted. We can adjust it so that micrometer gives us the maximum readings in our case, right? And all the photoelectrons that are ejected from this cathode uh, are collected by this collector plate B. Now, keeping the frequency of this incident radiation or incident light and the accelerating potential constant, what happens is that the intensity of the incident light is the intensity of this light along this cathode is increased. So by increasing this intensity of the light, we have what we observe is we obtain something like this intensity of light. Now, what we have to make sure is that the frequency has to be something greater than that of some minimum value, and then we measure the photocurrent. Then we measure the photocurrent using this emitter, and what we observe is a behavior like this. So what we observe here is that with the increase in the intensity of light, we have a proportional increase in the current. But what is important here is that there has to have some suitable frequency. We cannot have this graph unless we take on some minimum possible frequency of the light that we have been using in this case. So what is happening is that we are finding a proportional behavior. So thus I can say here that this current that we have along the y-axis of this graph, this photoelectric current is directly proportional to the intensity of light. In other words, I would say that the number of photoelectrons that are reaching to the collector that increases as we increase the intensity of light. Right now, the next important thing is effect of potential, and now let us see what happens with the potential. So now let us suppose that this collector B is at zero potential. Okay, so this is my collector A, and this collector A is at zero potential. Now, when the light is made to fall on this cathode, right? When the light is made to fall on this photosensitive plate, photoelectrons are emitted. They are they are emitted, and some of the photoelectrons which have sufficient kinetic energy, they reach to this plate A, and thus we have the photoelectric current, and that starts flowing in the external circuit. Now, keeping the intensity in my experiment, keeping this intensity and frequency of the incident light constant, right? But that frequency has to be more than that of some fundamental frequency. Otherwise, this effect is not observable. So what we do is we think of changing the potential across these electrodes, and keeping the intensity of the radiation that's falling on this cathode constant, and keeping the frequency constant. So and increasing this potential, this positive potential that we have, increasing this potential slowly at this electrode A, and measure the corresponding current that we have, that can be measured by this emitter. So what we observe here in this case is something like this. So this is the potential. Let me choose this as origin, and this is my y-axis, and this is my positive V, and this is my negative V, and the outcome comes something like this. Now, this is basically the positive potential. You can call it accelerating potential. And this is the negative potential. It's basically the retarding potential. So we have this kind of behavior. We observe this kind of behavior. And now what we see here is that this accelerating potential, if we start decreasing this accelerating potential, it remains there. The photoelectric current remains there. This is photocurrent. This is photocurrent. Okay, so what's going to happen here is that the maximum value of current that we have here is this, and we call this current as saturation current. As saturation current. And in positive potential, now if this is my positive potential and this is my negative potential, and if I increase this accelerating potential, there is slight increase in the photoelectric current, and then there is saturation. And now this increase is okay from the graph point of view. Now, what would I like to do is that I would like to decrease this potential. Now to decrease the potential that's applied across this collector plate to zero. If we take this to zero and then make it negative with respect to the plate C. As the negative potential applied to the B is increased, the photoelectric current goes on decreasing. Now what's happening here? It's not simply coming to zero, it goes on decreasing. For a sharply defined negative collector potential V0, the photoelectric current becomes zero at some potential. Let me call that potential as zero. Now this retarding negative potential, for which this photoelectric current just became zero, we call this as cut off or stopping potential. So this is cut off or stopping potential of electrons. And at the stopping potential, there is no photoelectric current observed. And the case is very simple, because when we have the positive potential, the electrons are emitted from here, and when we start decreasing this positive potential, so decreasing, it means this plate is becoming negative with respect to the positive. So the electrons, they reach to it, they overcome the electrostatic force of repulsion that is that's there with respect to this electrode A, which is becoming more negative as we increase the negative potential of the experiment. So still, as we go on decreasing this negative potential, still there is current, but this current is decreasing, right? And a stage is coming, we have enough reverse potential applied across this tube, where no electron is able to hit this cathode. So that is what the potential at which we find no photoelectric current. We call that potential as cutoff potential, right? So this is the concept of cutoff potential. Now, after this, we would like to see what we observe when we when we change when we use the light of different intensities. Now, so what we do is we do the same experiment, and what we assume is that we have let us assume that we have intensity I1 of the light, and if we now increase the intensity from I1 to I2 and then I3, such that this I2 is greater than I1 and this I3 is greater than I2. So, performing this experiment in a separate way, what we see here is that what we do here is that keeping the frequency constant and repeating the experiment by first increasing the accelerating voltage, and we find that the photoelectric current again attains a saturation value in this case, and what we observe in this case is something like this. We have this positive V and this is negative V. Suppose this is the origin, and we have photoelectric current, and what we see is something like this. The outcome of the experiment is something like this. The outcome of the experiment is something like this. Now this is my I1 and this is my I2 and this is my I3. Now we can see that the behavior can be explained. There is no problem with that. But the point here is that as we reverse the voltage, what we find that the lights of having different intensities, as we know this, we have I3 greater than I2 greater than I1. Even though the photoelectric current, the magnitude of photoelectric current for I3 is more, the magnitude of photoelectric current for I2 is more than I1. But what is strange here is that we find that the stopping potential for all the cases is same. The case in which I3 is greater than I2 is greater than I1. So the point here is that even though we use the light of more intensity, and we find the stopping potential same for all the three cases. This is what we observe experimentally, and this can be explained by virtue of the same explanation that we gave in the previous case, that by increasing the intensity of the radiation that we are using in this experiment, we are not actually increasing the energy of the photons, energy of the radiation that's falling on this photosensitive metal. They all have the same energy. So since their number is increased, but they all possess the same energy. That's why all of them have the same stopping potential, because in every case maybe the number of electrons in this case is more than that of this, but the electrons that are ejected from this cathode, they have same energies. So you need the same amount of work to stop all the electrons in all the cases. That's why the stopping potential is same in this case. Now, to move on from here, we can talk about the effect of we can talk about the effect of frequency. Now, what we are going to do is we are going to use the same experiment, but we are going to have different frequencies of light that we will use in our experiment. So in that case, if I perform this experiment and use three different frequencies, and this is my accelerating potential, this is my retarding potential, and and I start from same saturation in all the cases, but I have what I find is I find different stopping potentials. Now, so this is say V1, this is V2, and this is V3, and this is nu1, nu1, and this is nu2, and this has the frequency nu3. Now, what's happening in this case is that this is again my photo current. Okay, so these things can be understood, but as we go on seeing, for the different frequencies, we have different stopping potentials. So nu3 is greater than nu2 is greater than nu1, and what I find is V3 is greater than V2 is greater than V1 in the reverse direction. So what does it mean? Why we are observing different stopping potentials for different frequencies that are involved in our experiment, and the reasons for that can be assigned, that the curve having nu3 means higher frequency means higher energy. So the electrons that are ejected here with nu3 will have higher energy. So you need more stopping potential to stop these electrons. And instead, if we take this graph where nu1 is very, very less than nu3, so here the energy of the emitted electrons is going to be less than that of nu3. So in case of nu1, we will have to use the minimum potential to stop the electrons reaching to this plate A. So that could be the possible explanation for having an observation like this, in terms of different frequencies, in terms of different intensities, and defining the things in terms of the stopping potentials. Now, what should I to move forward from here? That's what could be the possible. These are the possible. These are the experimental outcomes that are observed while performing the experiment that we have here, and we observe these kind of behaviors. And in every case, what we find that frequency has a role to play, and we are not able to see this effect if the frequency of the radiation is less than some threshold frequency. So there has to have the frequency greater than that of some minimum frequency. So I should say that this threshold frequency for a given surface is defined as the minimum frequency of the incident light, below which no photoelectric current is observed in all the experiments that we have performed, right? Even though we could see from the very first graph between the intensity of light and it was proportional in this case. Exactly, increasing the intensity of light, we have a more photoelectric current. But the condition here is again that the light that we are using here, it must have frequency greater than that of some minimum frequency. Only then you can have this behavior. If we use a light with nu less than this minimum frequency, we are not able to see this kind of behavior of photoelectric current with respect to the intensity of light. So these were the experimental outcomes of this experiment, what's known as photoelectric effect.